All right, good afternoon, everyone. We'll continue with our discussion of circuit fundamentals. And then I believe some students have questions. So right at the very top, let's get those questions answered. Let's bring up the notebook. And okay. Okay, so what questions do students have? Yeah, go ahead. So number 5 on the homework. Let's see, dashboard. All right, 115. All right, 5 is total load in the schematic shows connected to a voltage source. The wiring has finite resistance. Determine the current supplied by the voltage source. The load is 10 and consumes 110 watts. The value of the parasitic wire resistances. And so you're saying for answer of part B, you obtain a negative value. What do we think a negative value indicates as far as electrical quantities are concerned? Let's say for current, for instance, if you obtain negative, so it's simply, so it's a, yeah, it's feeding not backwards, but it would mean that if we assume a direction for a current and we obtain a negative answer, it simply means that the flow of the current is the opposite of our assumption. That's all it means. And so when we perform a calculation on this one, current flow is shown. If it's not shown, the way we would determine it is from a source, current always goes from minus to plus. Meaning for this voltage that we see in here, current is going in the upwards direction. If it goes in the upwards direction, there is no other place for it to go except go from left to right and then make a loop. So as shown in the circuit diagram, the current's flowing clockwise, right? So our voltage drops across the resistors. Point of entry of the current is always positive, okay? So for our source, current goes from low to high, minus to plus. For everything else that is receiving energy, current always goes from high to low, meaning from plus to minus. For all the resistors, if the current is flowing from the top to the bottom, then the voltage will have a polarity of plus at the top and minus at the bottom. Okay, so can you tell me what polarities do you take for the voltage? Probably as assumption of the current flow might have been incorrect. That's mm-hmm. Okay. Mm-hmm. So V over I minus, no, V over I would give us the resistance, total resistance. And then you subtracted that with the load, and then you obtained a negative answer. Two different lines. And so that's why you obtain a negative answer. Is that what you're saying? So your total resistance turned out to be less than the load resistor. That's the only way it would be negative. Okay, I think I got what the issue was. Now let's see what the answers. Has anybody else tried to solve it? Problem number 4 yet? Okay. All right. So current supplied by the load is 10 and consumes 110 watts. So from first, if P is 110 and R is 10, we can use I squared times R. So I would be equal to root of P over R, right? P over R. And so the answer you obtained was 3.32, 3.32 amps. All right. So let's see. And then the square root was 3.32. Okay. And then once we have total I, source has a value of 12 volts. And so if it is 12 volts, let's actually solve it by hand. Oh, not the entire thing. Okay. All right. So what did we obtain so far? We have power is 110. We had R as RL was 10 ohms. And we obtain I. So I was square root of P over RL, which you obtain as 3.2, right? Just as a small matter, usually when I perform my calculations, I don't round up until like the 4th decimal place. So what I do is I write down 3.3166. Okay. Sometimes it does make a big difference. So there's sometimes the problems with very long calculations, and small differences like this can add up to like big changes in the final values. So I just go up to like 3-4 decimal places before I round up. Anyway, so that's 3.3166. So for the second part, voltage is given as 12 volts. So this is B, this is A, and 12 volts is being applied to RL of 10 and load is 10, consumes 110 volts. Okay. So then what do you all think we can do after this point? We have voltage, we have the total current, we have the load resistor. What equations come to mind? If we want to find the value of R line, what values come to mind? What things come to mind? Anyone? V equals IR. So what is the voltage across RL? RL is 10 ohms. We found I in sub question A. So what is VRL, the voltage across RL? What is that voltage? Sure, somebody can calculate and find out. How much? 33.106. All right. So this 3.316, okay, here's a check that we can make. What is our supply voltage? 12. So it is not possible to obtain a voltage that will be greater than 12. And that means that this is incorrect. Now, where is it incorrect? Well, this power is 110. So this is probably not amps. So let's do this. 110 watts divided by 10 ohms. Let's do it the other way. I squared times R. So I square is P over R, which is 110 divided by 10. And that should be 11. So square root of 11. So maybe that load resistance value might be incorrect. I'll need to check the question notes. Now if RL see, let's go back to the grade scope question. So this still does give me 3.3166 amps. So I multiply with RL, that gives me 33 volts, which should not be possible. So yes, go ahead. So that's what I'm gonna need to check with Protonov, see if there's an error in his notes. So it might be 120. So I need to find out. So I'll send an announcement or a post and announcement right after I verify with him, which will be sometime later today, if he responds. I'll solve this with 120 volts, and if it works out, then again I'll let students know either ways. So if you solve with 120 volts, then chances are it might work. Okay, any other questions? How many of you were able to download LT Spice and run the simulation? Did it work? In LT Spice or negative terminal? Mm-hmm. Negative terminal will be connected to reference ground. So it will just be 0 volts. So yeah, it'll just say this is node 0 or this is ground, and it'll be 0 volts. Yeah. Okay. So once again, as you pointed out, this is more could likely 120 volts. So if you want to solve it before I confirm it, you try 120 volts and see if it works. Okay, continuing on. Let's see here. All right. Ammeters and voltmeters. So slides notes it as ampere meters, because you're measuring ampere, but everybody uses the short form for this one, which is ammeter, AM. That's it. Okay. This ampere meters just means ammeter, or ammeter just means ampere meter. Now, what do we do when we connect a voltmeter or a ammeter to measure the voltage and current? You have two terminals, common terminal and the point of measurement. So there's a reference point, more often than not, color coded as red and black terminals. And common terminal is the most important because that forms the reference of the baseline for the measurements. For voltage, it's rather straightforward. We don't need to break a circuit because you're measuring between 2 points or across 2 points. So if you're measuring across 2 points, we can simply take the two terminals of the meter and connect it across those 2 points. So as shown in this diagram, in this illustration, we have two nodes across this resistor where we are connecting the voltmeter. Now, expected polarity would be, because this is a source, current flows in this direction, makes its way around, goes through the resistor, and comes back out this way. So point of entry of the current through the resistor is at the top. So it'd be plus and minus this way. So before we perform a measurement, we do need to visualize, or at least to understand the circuit and understand where the polarity is positive and where it's negative. And so we connect a meter according to that observation. Okay. So if you take the positive terminal of the meter and you connect it to the top end and the negative to the bottom end, we would end up with a positive voltage. The actual circuit is simply this. It's simply a source connected to a resistor. That's all it is. It's a source connected to a resistor. This circuit is unique, or anytime you have two components like this, it's unique because the two components are in parallel and they are also in series. Right? It's the same current flowing through both, and it's the same voltage across both. There's a unique connection. When you have two components connected like this, and there's nothing else in that circuit, they have the same current. Let's call it I, and they also have the same voltage, V. If you want to measure V, we simply connect, erase this. We simply connect the voltmeter in parallel to that resistance. You're measuring the voltage. Positive terminal of the meter goes to the positive terminal of that voltage, negative to the negative, and you obtain a positive value. For instance, if we didn't do that, and we just simply randomly connected our voltmeter, well, the meter will still measure the magnitude. If it's like 5 volts, it will show 5 volts, but it'll have a minus in front, so it'll show you -5. Simply means we connected the polarity opposite what it actually is. So now let me ask you the question. So we see this illustration, we have a voltmeter connected, right? So here there's a voltmeter connected. What happens when we connect a component in parallel to another component? The voltmeter is an electrical instrument, right? So it has some resistance. Now, if it has some resistance, what is it that we're actually doing? So if we connect connect a voltmeter, the electrical circuit could look like this. This is the original resistance R. And this is the voltmeter resistance, Vm. So what is happening? We have a electrical instrument. Between its two terminals, it has some resistance. So if we connect it in parallel with another resistor, now there is a possibility that the voltmeter could pull some current away from the source. And if that happens, then the current flowing through our resistance will be incorrect or will be lowered. And because that's lower, now it's going to be an incorrect voltage measurement. Okay, you're connecting a voltmeter in parallel to that load resistor. And so if the voltmeter resistance is not high, then the voltage being measured would be incorrect. So an ideal voltmeter should have infinite resistance. Again, the keyword is infinite. Okay, so an ideal voltmeter should have an infinite resistance, and thus it will draw 0 amps of current away from that circuit. And that's the property of a voltmeter. In real life, voltmeters, depending on their design, would have resistances on the order of like mega ohms. So if you're trying to measure voltage across a 100 ohm or 100 kilo ohm resistor, and your meter has a resistance of like 100 mega ohms, it's as close to infinity as possible in real life. Right? So it's not going to draw too much current away from your circuit. If it draws like picoamps or femtoamps, the voltage drop measured might be like dropped by like microvolts. If you're trying to measure like 5 volts, like microvolts of voltage drop loss would not affect your measurement. Yes. The question being asked is the desired property of the voltmeter to have such in high resistance, is it to limit the amount of current? The answer is yes. We want it to limit the current that it draws from the circuit, because if it draws more current from the circuit, it'll change the voltage across the RL. Okay. Similarly, if you have a ammeter and you're trying to measure current, the difference between a voltmeter and an ammeter is that the ammeter is measuring current. In order for it to measure current, current needs to pass through that meter itself. So we need to break the circuit. So you break the circuit right here. And insert the meter in the middle. Okay. Have you all done current measurements in 145? Okay. So you all learned how to break a circuit and insert the meter in the middle, right? Now, when we do that, the positive end of that meter must match up or be close to the positive end of the voltage source. The negative end must be away. So negative end must point towards the negative end of the source. Positive end must be connected towards the positive end of the source. Otherwise, again, your current, instead of being plus 1 milliamp, would be minus 1 milliamp. Okay. It seems like a small thing. It seems as if, let me just take the measurement. If it's minus, I'll just flip the sign. Well, that's well and good. But what if we don't know? What if it's a circuit? You're simply analyzing an actual real life circuit. You don't know where you're connecting. You don't know whether your answer should be plus or minus, right? So you simply connect a meter, but you need to first observe the circuit. The positive end of the meter must be connected towards the positive end of the source. So the current that's passing into the meter must go in from the positive terminal. So it goes into the meter and out the negative end and into your load resistance. So now, as it says on the statement, an ideal ammeter will not sustain any voltage, meaning the resistance of that ammeter must be as close to zero as possible. So when it says sustain no voltage, it means the resistance of the meter must be 0 ohms. And diverting no current would mean the resistance of the meter is infinite ohms. 0 and infinity. In real life, the same meter that we use, digital multimeters, depending on the mode of operation. If you use it as a voltmeter, it'll have infinite resistance. Sorry, not infinite, very high resistance. And if we use it in current measurement mode, it'll have very, very low resistance. That low resistance would be as close, practically close to 0 as possible. Okay, it'll divert very little current, microamps or less. Okay, that's the desirable property of a voltmeter and an ammeter. Sorry, not this way. This is the resistance of the ammeter. Now, obviously, if the ammeter resistance is even a little bit high, then the current, it will cause the current flow through here to drop. And if it drops, then a voltage will appear. The only way it cannot affect the circuit if the resistance of that ammeter is 0 ohms or as close to 0 as possible. All right. Okay. Let's move on. A few more examples that pertains to the homework. All right. So we have a 12-volt battery. The battery is connected to a 100-watt load. This is, again, something that we looked at previously. Right now here, we are saying a battery or anything, but could be anything, right? Could be a benchtop power supply, could be a adapter, laptop adapters, mobile phone chargers. Loads could be anything. Again, load could be your laptop adapter, your mobile phone chargers, could be DC motors, LEDs, speakers, could be anything. All right, so in this case, we are connecting 12-volt battery to 100-watt resistor, and then we saw how we can calculate the resistance using P equals I squared times R, P equals V squared over R, right? That's also what the homework tests you on. So ideal wires do not have any resistance. Practically, wires do have resistance. They will cause opposition. Any current carrying conductor, or any conductor for that matter, any cable, any wire inherently has resistance, it has capacitance, and it has inductance, R, L, and C. If I pick up the cable, if I pick up this USB cable that you see here on my desk, that inherently has some resistance, it has some capacitance, it also has some inductance. The thing is that the value of this resistance, inductance, and capacitance is very, very small. It does not rise to the level of interference. If I'm using this USB cable to transfer data or connect an instrument to a computer, the resistance that this cable has is not so large as to affect the operation of that data transfer. Does that make sense? Theoretically or hypothetically, when we are performing analysis on paper, that analysis ignores any resistance of the wires. In real life, we must consider the resistance of the wires, but only in certain cases. Again, as I said, this USB cable is what, 3 feet or less. And so whatever resistance it has, 3 feet, it's not going to affect it. Now, if I increase the length of this USB cable to 100 feet or 200 feet for that matter, now that resistance could perhaps affect the transfer of data. Okay, so it depends. So those are the kinds of considerations we need to take into account. Yes. So the question being asked is, are there wires that are bad or conductors that are bad that still work? So conductors that are bad, like say with old age perhaps, or low quality, you mean? Yeah, they are still used. So as an example, I would say power extension cables. Okay. Anytime we buy an appliance, let's say like a space heater, right? If I bring like a radiator style electric heater and I plug it into the wall, the manufacturer has ensured that the cable or the wire cable that it uses is usually typically very short. One of the reasons it's very, very short is because that electric heater is going to pull a lot of current, a lot of power from the power outlet. And so when you're pulling a lot of power, the voltage is the same, but it's going to pull a lot more current. The higher the current that passes through that wire, the hotter it's going to get. And so you want to limit the amount of cabling that they use because you don't want it to get too hot, right? So the longer it is, the more money they have to spend to create a cable, to have a cable in there that is able to sustain that high amount of current. There's also always a warning. Do not use an extension cable with this heater. Have you ever noticed it? The reason is because people might just buy an extension cable without looking at the spec, right? And sometimes some manufacturers might have like, okay, yeah, this cable can handle like 200 watts of power or 500 watts of power or whatever. But it's not, you need to have a little bit of technical knowledge about it, right? So you take an extension cable, 10-foot long extension cable, and you plug it into the wall and you put your heater 10 feet away just to reach its space. Well, now a whole bunch of current and power is transferring 10 feet of cabling. If that cable or the wires, the conductors are not capable of carrying that amount of current, it's going to get hot, it's going to melt, insulation melts, shorts of the two wires, and your fuse or your circuit is broken. You might start a fire. So bad wires and bad cables would still work, but it depends on the application. That's the answer to the question. Okay, so USB cables, there are some high quality USB cables. There are some high quality HDMI cables. If you want to plug in, let's say, like a display device, like a projector like this is routed through a very long wire connection, right? So in this room, you see these projectors. There's a wire that runs all the way through into, and then I think it goes through, not through there. I think it all goes to a central receiver somewhere in the wall. Okay. And so right now, the setup that I have at least a 10-foot HDMI cable that is going from the computer on the cart into the wall. From the wall, it's again running another 10, 15 feet going inside. There's a box somewhere in there. And that receives the signal. Well, this cable must be high quality. Otherwise, it's going to affect the transmission of the data. So if I was to use a cheaper cable, well, not me, but a cheaper cable was provided to us, it might not work. So there are some instances where the resistance or the capacitance or the inductance of a cable will interfere with our operation. It just depends on what our operation or application is. Okay. And so that's what they're talking about. What is the impact of the resistance of the wires? Well, the impact depends on the end application. Our end application is simply to take 120 volts and transfer it 100 feet away. Even a cheap cable would work fine. All I'm going to use it to charge my phone. Not a whole lot of power is transferring over that 100 feet, right? So it's going to work fine. If I plug in a space heater on that same cable, it might not work. So again, the application is different. So the resistance of the wires, how does it impact? Well, it impacts in by slowing. First is lowers the current that's flowing through there. That means it causes a voltage drop across that entire cable. So it's dissipating and consuming some of the power. And the other thing is safety considerations, meaning if it's low quality, it's going to overheat. If it overheats, it will melt the insulation in the cable and then causing a short circuit. Okay. So let's see. Oh, these are just examples of like typical resistances over like a kilometer of that kind of cable. So 1,000 meters, 1 kilometers, you have about 84 ohms of resistance in a standard wire. On a slightly separate note, what happened here? Why is it not? Does anyone remember the definition of resistance or equation for resistance from physics? Is this something that you have done in physics? No. Yeah. So resistance R is resistivity times length over area. So if you have a piece of material or a wire, we take the cross-sectional area of the wire, that is A. This is A. This is the length. Greek letter rho defines the resistivity of the material of that wire. So you can see the longer the wire is, the higher the resistance. And the thinner the wire, the higher the resistance. So if you want to transmit something over long distances and you want to reduce the resistance of the wire, you need to spend more money on the copper, well, not copper, but on the metallic conductor that is carrying the data or carrying the signal. So that makes it more expensive. Okay. Oh, by the way, these gauge sizes, the lower the gauge, the thicker the wire. Okay, just a practical consideration. The higher the gauge, the thinner the wire. Okay, so we looked at this problem where we applied KVL and KCL, calculated the total power. And then let's see, total power delivered. So this was the problem, not problem, similar to the problem in the homework. We are applying a source. Source is going over cables. Sorry, the current is flowing over cables that have 50 milliohm resistances, and 50 milliohm resistances are going to dissipate about 3 watts of power. 3 watts of power each. Right? So if it's totally supplying 90 watts, well, 6 watts is lost in the power. And then we did this. Let's see. So this is the results of the SPICE simulation, right? So if you have a circuit created in LT-SPICE, always requires a ground label or ground node, which is labeled right here. And what LT-SPICE is going to show you at the bottom left corner, when you hover the mouse cursor on top of a specific node or along that wire, It's going to show you at the bottom left corner, the status bar at the bottom. This is node 001. This is node 002. Or if it's a ground node, it's going to say this is ground G and D. And the value of that voltage will also be shown 0 volts. Okay. We can also note and mark the voltages directly on top of the circuit diagram. So if you take your mouse cursor and you click anywhere along this line, it's going to show you the voltages or the resulting voltages. So there's a way to do that in LTSpice. If you just hover the mouse cursor, it's going to show you the voltage. If you want that voltage to appear on the circuit diagram itself, you can simply click on the wires or the nodes. It's going to show you that voltage. So voltage here is 12 volts. But when it goes across the line, it measures from this point to this point. So this 11 volts is measured again with reference to ground between these 2 points. So before reaching the load, it already has lost some voltage, right? This is the voltage that is being applied to the load resistor, 11.61, because some voltage is lost in the line resistance. Same thing happens on the other side. Our load, this is going to take up some voltage, and because it takes up some voltage, the load resistor only has 11.6 minus 0.38. So this voltage, 0.38, is again measured with reference to your ground node on the left. So if you have done this simulation correctly, you should have these similar answers as shown in the slide here. If you have not yet done it, well, now you have the opportunity to do it. And so you already know the answers that you expect. Hey, we already did this. Why? Okay. All right. Single voltage source supplying 2 loads. First, let's use a practical example. On each row that you see here, we have these power outlets, right? Each power outlet stand by itself has 6 outlets. Okay. So let's say there's one over there, there's one here, one here. So front row has like 3 times 6, 18 power outlets. All 18 of them are in parallel. The second row has 1, 2, 3. Again, second row has 2, the third row has 1, the last row has like 5, right? No matter how many outlets we have, if you look at the floor, there are these circular outlets, and they're all plugged into those circular outlets. Now, underneath the carpet, there are pipes. You see these metal pipes running on the top? They have similar pipes running underneath the carpet, and they are all in parallel. Okay. Anytime we plug in any device into these power outlets, they are all in parallel, meaning the ground wire. So we have 3 components of a power outlet. There's a ground, there's a hot, and there's a neutral. So let's say ground, plus, and minus. All of these 3 wires are all running in parallel. Okay. So if you're trying to connect it to a source, let's say the source is a power outlet. All power outlets that we see everywhere around us, in residences, in commercial places, businesses, anywhere, they are all in parallel. They're all tied, depending on the distribution setup, they're all tied to a single circuit breaker. So if somebody's device does something at the front row, it's going to cause if it's not a separate circuit, if it's all the same circuit, then it's going to trip and turn off the power in every single power outlet. Okay. The lab benches too are all plugged into the same parallel lines. So if you look at the back of the wall, you have these power outlets coming from the top. They took it all the way on the other side of the wall, and they're going down and all along the back wall underneath the lab benches. And you can see that they're all in parallel. Nothing is separated out. So that is by far the most common way to connect a load, which is in parallel. They're all in parallel. So power outlets are all in parallel. Okay. And then we can take it to higher levels. All power outlets here are in parallel. If you take this room and we take the other room, the circuits that are coming into the building are distributed all in parallel. So you have one big wire coming into the building, or one big cable that brings the 3 wires in, and then it's distributed to every single room. Now, when it gets to every single room, it's broken down. Because it's in parallel, we want to protect. So let's say we have this main wire. And this is not like the central power station. I'm just saying this power station or a power distribution circuit outside a building. So power distribution box, it's sending it inside a building. And so now it's being divided. Actually, I shouldn't have drawn it this way. Let's do it this way. 1, 2, and 3. So it goes in here, it goes in here, it goes in here. Each one of these are rooms. And so let's say this is room 1, this is room 2, this is room 3. So each one of these circuits, they're all in parallel, but if we want to separate it out, what we do is we put a circuit breaker. Individual circuit breakers right here. So there are individual circuit breakers that protect. So if something happens in one room, it trips the circuit breaker and disconnects that room from the rest of the power outlets. So as long as you have circuit breakers everywhere, then we say that those are independent circuits. Okay. I am not sure if this room is on a separate circuit breaker or not. Typically, it should be. But I'm not sure. But does that make sense? We could have individual circuit breakers on every single one. Yes. Circuit breakers. There's a kind of like a solenoid relay in there. And then when it shorts, let's say if something happens, resistance goes low and it shorts and it triggers that relay. And so the relay is like a switch. Yeah. It's like a switch. And so that switch gets activated and so it breaks the connection. Before circuit breakers, we had fuses. So in vehicles, we still have fuses. Fuses are nothing but a very thin wire. It's rated to carry a certain amount of current. If the current that passes through the fuse wire exceeds its limit, it melts the wire, thus breaking the connection. So we say a fuse is blown. Well, the fuse is blown is there's a very thin wire, just melt it. That's all. So every time your fuse would blow out, you'd have to buy a new one and plug it in. So then came along circuit breakers. Circuit breakers were expensive and they were early on, but now they're very cheap. So it's far easier to install a circuit breaker rather than running and keep a stock of fuses, electrical fuses. So review this slide. This is the one way to connect connect 2 loads to a source that is in parallel, and the other way is to connect it in series. Okay. And connecting in series, real life example would be kind of like our holiday lights, where you have a string of lights and they're all connected in series. So the same voltage, the same current passes through all of them and the current remains the same. Okay. So we are in a rush at the end. So make sure you review these 2 slides. And then our quiz on Monday will be based on the material we have covered in these 3 days. Okay. All right. Have a good weekend, and I will see you all on Monday.